Okay, hope you guys could see the slides. And my name is Yamal from the Imperial College London. Today I will give a talk about exploring hypothetical reasoning in 3D. That is the work I done in the PhD, and under supervision of my supervisor Christian. He also comes today, makes me a little bit stressed. So before I start, I will talk a bit about the motivation of the paper and to give some brainstorming. So as we know, as humans, we can reason through the scenarios even without incomplete perceptual knowledge, and we can use our human imagination to bridge such kind of the knowledge gaps. So let's look at this conversation between these two persons. And if one guy said, okay, if one apple is taken away, and how many apples on the table? So even there, the thing show there are the two apples on the table, but actually we can use our imagination to think about, okay, after one apple is taken away, the answer is going to be one now. Yeah, and such kind of the ability is actually inherent in the human, and we call it the mental imagery ability. So to some extent, as a human, we feel like the imagination is to some extent more important than knowledge. Yes, so actually here we find out the more practical case study about when we can use such kind of the hypothetical reasoning ability. So well, in the 3D reasoning scenarios, and real-time access to the accurate thing is often limited by the several challenges. For example, the specialized equipment requirements. We need to use RGBD cameras or lasers to crack the things, and also the prolonged scanning time, and more importantly is the complex reconstruction processes. All of those challenges means that we don't really always have the real up-to-date things. So here we propose to define a new task. It's called a Hypo3D task. So we want to use in a context chain description, and we ask the models to imagine the chain thing and adjusting their reasoning accordingly. Yeah. So here's I give an example about our Hypo3D task. So for example, here we given the 3D thing, and we define the thing orientation to let agents know where is left and right, front and back of things. And the context change. The example is that the white table has been moved from this left to the coffee table to the left of the coffee table. And the question is, what is currency item position to the left of the white table? Before the change, the answer should be the seat. This one brown seat. And after the change, the answer should be changed to this green coach. So that is how the Hypo3D task works. And we're trying to define this task and evaluate on a bunch of different foundation models, including the 3D vision language model, 2D VLM, and also the large language model. So the first thing about this pie chart, we define the context change, and we define 5 different kind of the object level changes, including the movement changes, addition, attribute, replacement, and removal changes. And for the movement changes, for example, we move an object from one location to another location. Yes, and all of the changes are defined in the unambiguous way, and make sure all of the changes are spatially repeatable within the 3D thing layout. And apart from the changes, the next thing we define is the question and the answers. So here we define the 3 different types of the questions. It is called the scale and direction question, which focus more about the spatial reasoning. And also the semantic question focus on more attribute questions. And when we define this question and answers, we need to require all of those answers need to be required using both the thing and the context chain to answer the question, not only just using either of them. And the second thing is that those questions cannot be inferred from the common sense knowledge. Yes, for example, which one is larger, the bed or the pillow? Because in most of the cases, the bed is larger than the pillow, so it's not really meaningful to ask those questions. And the last thing is that we need to make sure each question is unique and ambiguous. And then here is the entire data generation pattern of the Hypo3D. We first collect the things and annotating the frames. And then we spend quite a lot of the workload on the context chain preparation and QA preparation. So here we are using the large existing vision language model to annotate it, and also followed by the crowdsourcing human resource to refine the result and spend kind of the half a year to crack the entire data set. So after we have the Hypo3D benchmark, we evaluate on the bunch of the existing foundation models, and we got some insights. The first one is the existing models still show the very huge gap to the humans. Yeah, for example, like a human, we can achieve the 90% accuracy of all type of the changes, but actually for the models, even the best performing one is still just 45% accuracy. And the models especially perform really bad on the movement and replacement changes. That makes sense because those kind of changes really changes a lot of the spatial relationship between the thing, and it is most challenging. And the last thing is that we found the model is struggle with the spatial question, and within the spatial questions, especially on the direction-based question, it performs really bad, based on the figure that shows at the right. And another insight I got is the reasoning in this kind of hypothetically changed thing is more challenging than unchanged thing. So here we define two different settings. One is so both of settings we are trying to ask the same questions, but one is with the change and one is without the change, and then it needs to give two different answers. We found to reasoning in kind of the hypothetical scenarios, all of the existing models performed really bad and showed a big performance drop. And another insight we got, those models also show the strong hallucination when the changes are relevant. So, for example, if our concept change is a cup is moved from table to the chair, is an object movement, but our question is what the color of the cup. Actually, we know that those kind of the object movement shouldn't really change the object attributes, so they shouldn't change the answer. But actually, we found that all existing models they consistently to address their answers incorrectly, and show the performance drop again. Yes, so basically here we show several results to show that existing model performs really, not only just the visual language model, also large language model performs really bad on the Hypo3D task. And one of the key reasons probably because those models doesn't really find a good way to represent the 3D, and the features are for this kind of the 3D understanding doesn't really helpful to this kind of spatial imagination. Yes, so here's we doing such kind of the following work. So for using the map to encode the 3D features, and we designed a framework called Comma 3D. It can be applied for the different kind of 3D understanding tasks. And once we apply this kind of point map into the result, you can find out, okay, on the challenging Hypo3D task and our point map based representation learning framework performs much better compared to the previous method, and especially on the challenging scale and the direction questions, its improvement is largest compared to the method using the point cloud or the depth map as the input. So here's I want to give a summarization of the work. The first of all, we propose the Hypo3D benchmark is to trying to evaluate the model's ability to perform reasoning without real-time scene access. And second, existing large language models struggle to not only understand how the scene changes to affect the answers, but also they don't really know whether such change is relevant to the reasoning. And the last thing is that we have given our insight we need more capable 3D representations with stronger spatial imagination on the spatial Hypo3D task. So one of the promising solutions we can do is using the point maps. Yes, and thank you so much. And if you have any questions.
Hi. For the representation and mapping of the general space that you provided as context to the LLM, right? Did you immediately start with a 3D representation, or did you start with simple abstractions to see how it performed against those?
Actually, we tried different 3D representation. So based on the results here, all of the models using various different inputs. Some of them using point cloud, multi-view images, also the top view images, and scene captions. And we showed actually the way to represent the scene is different in how to use.
Okay, yeah. But I mean, like particularly, for example, like really abstracting in a different direction for an LLM, for example, like using a 2D, like a two-dimensional map of a vertical area of that space to like sort of represent spatiality between objects, right? Was that explored at all, or would you think that's worth exploring at all?
You mean the scene graph?
Yes, yeah.
Yeah, actually, that's the thing. Actually, the existing visual language model, they can't really extract very complex, very comprehensive scene graph from the entire scene. They only can know, okay, within the image, they can understand the scene graph to some extent. But for the entire 3D scene, it's too challenging for them.
Yeah.
It's still a very long way to kind of scene graph. So actually, there's several different solutions to solve this problem. If we have a perfect scene graph, for sure, we can solve this problem. But actually, for nowadays, the still need to explore.
Fair enough.
I had a similar question. I think it's to this. So you can think of it's really good to see this benchmark. There's like three different problems that can be. One is given the scene graph can you predict the changed scene graph? Then, given the scene graph, or the changed scene graph, can you analyze give an answer to the question being raised? And the third one, which is what you mentioned, given the image, can we extract the scene graph? In your experience of the third one, like image to scene graph, is the one that's blocking us now?
Yeah, it is one of the blocking, and actually we also do try them. Here's for the 2D vision language model. We're using top view map. It's one of the useful way to extract the scene graph. Like still, actually, if we feed it into like the multi-view images, the scene graph is just totally wrong. But if we using top view map as an input, actually they can't really helpful to extract the 3D information. So they can't really understand the 3D relationship. They only understand the 3D.
Okay, let's thanks you again.